So we don't have too much time left in terms. Well, actually, we have plenty of time left to cover all the material. But in terms of like labs, don't have too much time left. I think we've got this week, we've got next week, and then Monday, I believe. Or I think Monday or Tuesday is is Monday the last day of class, or is Tuesday? I think Monday, because we lose a Monday in the first week, I think. And then you've got the study. Then you've got like a short study period, and then you've got your final exams. So be sure to demo everything before, before the final exam, because I pretty much turn into a pumpkin and disappear as soon as I hand out your final exams. Also, this exam will be a common final. And I will basically, so your final is pretty much going to be almost exactly the same as the other classes, except we decided that we can each change a question or two in the final exam to make it to gear towards stuff that I taught in my class. So I'll give you a heads up on my stuff, but otherwise the final is pretty rigorous. That's essentially, there's not too much left. I think I'll give out Dijkstra's as an assignment, and then I've got one other assignment I want to give you guys. Dijkstra's, implementing Dijkstra's can be a bit of an overhead. And the other thing we're going to implement, the last program will be a security problem. That'll be interesting. It's a graph problem, but it looks like a security problem. So today we're covering, as I mentioned, we're going to cover how we implement graphs, and I went over a bit of that, but I want to kind of go over why do we have two different implementations, and the answer you might surmise from the fact that we have two different implementations of a bunch of data structures is that one is better than the other for some situations, and the other is better for for different situations. So as I mentioned last time, we have two primary representations. The first is an adjacency list, which we represent. Basically, we just keep a list of all of our we keep a list of all the nodes that we are adjacent to. So if I've got a graph like this, where I've got A, B, and C, and then I've got D all by itself, my adjacency list might look like this. It might be a map where A is the key, and the value here is A is adjacent to B, B is adjacent to nothing, C is adjacent to B as well, right? Because you can go from C to B, and then D is adjacent to nothing, right? And we might, if you add another node, another edge, another directed edge in this case, C goes to A, so we add A into that list. We went over this last time. It's not really too hard of a concept, right? Adjacency matrices, and I put this on here because the adjacency lists are, they have it as a linked list, and it's a bit hard to read. But remember, for undirected graphs, let's zoom in here. So for an undirected graph, right, if 0 is adjacent to 1, 1 is adjacent to 0, right? So in a directed graph, you don't necessarily have that guarantee. In adjacency matrices, we use a 2D array to represent the graph. For an unweighted graph, so unweighted graphs are going to be treated a bit differently than weighted graphs. For unweighted graphs, we can use either a 2D array of booleans or a 2D array of integers. It's actually better to use integer values because some higher level graph algorithms can use matrix multiplication on a bunch of unweighted graphs or an unweighted graph to figure stuff out about that. Because if you've got an array of zeros and ones, that makes it, a mathematician looks at that and goes, I wonder if I can do matrix operations on this thing and get useful information out of it. And sometimes they do. So for here, we would we would use, a matrix, and it would look like this for an undirected graph. Let's see, so we've got A, B, C, D, and we've got A, B, C, and D. And I've got terrible drawing skills, but we'll have to make do, right? And then, so for, so can't get to, we have no self-directed edges. Well, actually, let's throw them in. An edge goes from D to D. That's perfectly valid. A goes to B. C goes to A. And C goes to B. And nothing goes to D. And D goes to nothing. And B goes to nothing else. And so that's what the matrix looks like. Okay, just a zero. If an edge exists between the two, then we put it down. If it doesn't exist between the two, we put a 0 in. Now, for weighted graphs, it's a bit different. Weighted graphs contain, unsurprisingly, weights. Right, that's possibly the most earth-shattering thing you've heard today. So weighted graphs contain weights. 0 is a valid weight for weighted graphs. It means you can transition from here to here for free, right? No toll, essentially, on the road. So instead, we use double dot positive infinity to represent no edge because, oh yeah, you can get from B to D. It's just going to cost you an infinite amount of whatever unit we're measuring. So that way, and so when we go through the algorithms that we need to, it ends up being the same thing. Discount those edges, or we say that it takes an infinite amount of cost to get from here to here, which means there's no way to do it. And an unweighted graph, instead, we could use just 1.0 for the presence of an edge. So it also depends on whether you're using a directed graph or undirected graph or a directed graph. We can be a bit more space efficient with a directed graph. With an undirected graph because because A to B in an undirected graph, we don't have these arrows. Right? In an undirected graph, we would have A goes to B, these three things would go to each other just perfectly fine. A would go to B, B would go to A, B and C connect to each other, C and B connect to each other. So instead, we could use just the lower triangular form of the matrix and just save that bit. So here's two adjacency matrices for two different graphs. So here in a directed graph, right, 0 to 1, 0 to 3, right, so we've got, 0 goes to 1 with a cost of 1.0, 0 goes to 3 with a cost of 1, 1 goes to 4, and so on and so forth. So one of the questions on your final exam will be given this, right? Given this, this adjacency matrix, please give me a graph, okay, that represents that. So, please draw the graph that we get from this. And here in this, for this one, because it's undirected, technically we only need to save this portion of it. We only would need to save this because notice how it's symmetrical. All right. So now the question is, what do you want to use a directed graph or an undirected? Sorry. When do you want to use an adjacency list or adjacency matrix? So that really depends on what implementation you want to use depends on basically the density of the graph. And what does it? So for a dense graph, you're looking at basically. So the idea here is that basically, notice in this adjacency matrix, we've got a list of all possible combinations. So all possible combinations of edges, right? We could go. you know, we could have a possible edge from A to A, and then A from B, and then A to C, and then A to D. Those are all the possible edges in a simple graph, right? In B, for B, we've got all the possible edges of B goes to, you know, B could go to A, B could go to C, B could go to D, and B could go to itself, right? So those are all the possible combinations in a simple graph, the graphs we're looking at, and so on and so forth. In other words, there's V squared possible combinations, right? There's V squared possible edges that could exist, right? Now, adjacency matrices list all of them explicitly. Either that edge either exists or doesn't exist, right? But we'll use this as whether or not we have a dense graph or a sparse graph. Now, dense graphs are ones where basically most of these would exist. So something like a clique, where all the things in here would be 1 or close to 1, right? So we might have a graph like A, B, C, and D, right? And so here's that, and then basically everybody else but A connects to D, right? That's close. That's what we would refer to as a dense graph, because basically almost all the edges exist. A sparse graph is basically means where, you know, every node has basically one edge. And so dense graphs, you basically are closer to the number of vertices squared number of edges, and sparse graphs, you're closer to the number of, you know, there's like about 1 or 2 edges per vertex. Yes?
Is there a reason they're implemented separately in Jung?
In Jung? Because depending on your like an array list or
there's a sparse graph.
Right. So sparse graphs will use the adjacency list, and dense graphs will use adjacency matrices. Because depending on how sparse it is, it's better. So most of the graph algorithm we're going to see are of the form of, for every single vertex in the graph, we're going to look at every single vertex in the graph, and then for every vertex that's adjacent to, so for every other vertex adjacent to the vertex I'm looking at, so like for each node, look at each one of its neighbors, and then if that neighbor exists, do something for that edge, essentially. So in an adjacency list, we're looking at basically the step 1 is, the outer loop is for every vertex in the graph. Step 2 is for every edge that's next to me, do something to that edge. So essentially this goes over every single edge in the graph. So so in adjacency list, it's this algorithm will run, you know, it will run a step for every single edge in the graph. That makes sense, right? This literally says for every vertex and every look at the nodes it's adjacent to, right? The nodes are adjacent to are the ones that it has edges with. So this will take O of E time. So for an adjacency matrix, on the other hand, what you're going to do is you got to look for every node in the graph. Then you have to scan through all your row in the matrix to find all the stuff you're adjacent to, which is O of E time. So this would be O of E squared time, because you're looking at for each vertex, you're looking at all the possible entries. You're looking at all the possible edges that could or could not exist. And then you look at the edges that do. And what we find is that adjacency lists are better at dealing with the sparse graphs, right? Because if O of E is, right, because O of E, that's either V or that's V squared, right? This is either V or V squared. It's V in a sparse graph, V squared in a dense graph. And adjacency matrices are V squared, no matter what you do. So adjacency matrices, though, they're useful in a dense graph, because you just can scan through the entire matrix just like in a nested for loop. But if you're scanning over primarily edges that don't exist, it's better to use an adjacency list. Also, you're using up plenty of space here for all those edges that don't exist if you're using it for a sparse graph. So So adjacency matrices are just better for I mean, we can look at this for other algorithms, but matrices are better for dense graphs. Sparse graphs are better for it's the same for sparse essentially for this one. The other thing again is storage, right? You're using in adjacency matrix. You're using a lot of it's useful if you're basically using it in a dense graph because remember, using a space for every possible edge. In adjacency list, you're only using it for the edges that just exist. But you also have to store references to everything because you're storing it in a map, which if you're using it as a hash map, that's going to have also be wasting memory as well. So you got to keep that into account. So adjacency matrices in a dense graph, they're much more storage efficient. So is there like a kind of a cutoff point where we should use it? Yes. So here's like the important slide. The break-even point is when 25% of an adjacency matrix is filled with, non-zero or non-positive infinity data. In other words, if 25% of the possible if 25% of the possible edges exist, use an adjacency matrix. Otherwise, use an adjacency list. So 25% is the cutoff point. That's the most important side. Yeah, we went through a lot of theory, but this is the practical implementation. And if you're and this is like what you'd want to remember. Okay, so now let's get away from the boring stuff and actually look at the interesting things about what we do with graphs. So just like we had tree traversals, a lot of algorithms work off of traversing a graph to find something interesting. Like maybe you can't examine all the things in the graph, right? So we want to go through a graph and maybe find something. Typically, this is to see if a node is connected to another node or if this node exists in this graph, or to find a path. And you're either going to go through this in breadth first search or depth first search. And believe it or not, the algorithms are pretty much the same. They're pretty much the same algorithm. We've gone through them before when we were going through the maze thing. So this is actually a nice review for you guys, right? This isn't too unfamiliar because we've done this with mazes. But the only difference between these algorithms is breadth first search is going to use a queue, and depth first search uses a stack. Otherwise, it's the same algorithm. So first in, first out versus last in, first out. So breadth first search simply works like this, and I think I went over a bit last lecture, right? But I don't mind going over it again because it's kind of important. We choose a starting point. We choose a starting point on our graph. Okay. So here's our starting point. I typically label our starting node S in my examples. Okay, S for start. And then we look at all of S's neighbors. Okay, so we explore all of S's neighbors. And then the next step is we explore all the neighbors of those neighbors. Here's this guy only has one neighbor. Okay, and then the next step after that, we explore all the neighbors of these two-step neighbors. So I explore all the people who are 3 steps away from me. So maybe he has 3 neighbors. Maybe this guy has these neighbors. This guy has neighbors. And this guy has a bunch of neighbors. So, and then the next step would kind of be obnoxious to draw, right? Where we explore, where we explore 4-step neighbors. Essentially, we start by looking at this guy. Then we look at all of his neighbors, right? So these are all what we would call 1 step away. Then all these guys over here are 2 steps away. And then all the guys floating off the 2-step neighbors are 3 steps away. Right? How many of you have ever played 6 Degrees of Kevin Bacon? Right? 6 Degrees to Kevin Bacon. Anybody familiar with that? Yeah. What's the premise?
Is it you go on Wikipedia and you try and find Kevin Bacon?
It's close. Yeah, it's close. But that's another great example though. That's Wikipedia race kind. So with What are you gonna say?
Kevin Bacon or somebody who's been in a movie?
Yeah, Kevin is a pretty prolific actor. So in other words, he's been in a lot of roles with a lot of different people, right? So the question is basically, can you from this arbitrary person get to Kevin Bacon in basically 6 steps, right? In fact, our actors sometimes have what they call a Bacon number, which is the number of steps removed from Kevin Bacon they are. So if you've acted with Kevin Bacon, you've got a Bacon number of 1. If you've acted with somebody who's acted with Kevin Bacon, you've got a Bacon number of 2. And if you've acted with somebody with a Bacon number of 2, you have a Bacon number of 3. Yes?
And if you are Kevin Bacon,
You have a Bacon number of 0. Right. So mathematicians have something similar called the Erdos number, where if you have published a paper with Paul Erdos, you have an Erdos number of 1. If you publish with somebody with an Erdos number of 1, you have an Erdos number of 2, and so on and so forth. I have an Erdos number of 5. So, yay. And then some people have an Erdos Bacon number, which is if you have a Bacon number and an Erdos number, it's the higher of the 2. So, so the other thing is, as you mentioned, like Wikipedia arrays, which is, although that can be much more of a depth first search kind of deal. Wikipedia arrays, typically what you're doing is a depth first search where you're looking down a corridor to see if you can get from one Wikipedia page to another, like from World War II to hospitals, or that's not too hard, right? World War II, and something that basically, let's say, Teenage Mutant Ninja Turtles, right? How can you click on links to lead to another one? Another fun, popular graph kind of game on Wikipedia is basically the premise that if you click on the first link of any Wikipedia page, it will bring you to philosophy eventually. So Wikipedia, let's look at graphs on Wikipedia, specifically right maths. Yeah, so here we are on the graphs page so this is all about graphs. Graphs it's pretty well found on Wikipedia, but if we click the first page, so first thing in mathematics, that'll bring from the Greek, forms of Greek, modern Greek. I'm not sure if I'm supposed to include the parentheticals. So, whoops. So colloquially, everyday language, but has other meanings. Right, you can click the first link and, native language, language is a system of communication, meanings, semiotics, meaning making, psychology, science, knowledge, and then facts, and you can see how we're getting closer to philosophy as we
go back. Go back to science. Or knowledge.
Knowledge.
It's right there.
Knowledge is familiarity.
Second paragraph.
The premise though is if you keep clicking the first link. I'm not sure if it's in the parentheticals or not, but eventually you will get to philosophy in a lot of things. Some things they have self-contained loops, so some pages that doesn't work for. But basically seeing if you click on the first link and that eventually brings you to philosophy, and then building a tree that does that, that's a graph problem. Let's go ahead and see. On first link in Wikipedia, Sophie. I think people have built like so getting to philosophy. So this is somebody else showing that basically if you click on, so science goes to knowledge, goes to awareness, goes to consciousness, goes to consciousness, so consciousness, quantity in philosophy, and then philosophy. So this is just basically, this is a graph. Although technically, it's a graph.
One of them is C++.
Yep. So I wouldn't be surprised. Yeah, C++, programming language, formal mathematics, quantity. So I don't think I was supposed to click on the first parenthetical. So, but that's fine. But as you can see, this is a graph problem, and building this up is a graph was basically required, knowing how to do graphs. It's just one of those neat things that you can do. And it gets into this small world networks, which is something I studied during my PhD, which is kind of crazy, but it describes the way, does it not have a picture of it? of like basically it describes the way that networks build up. But anyway, let's go back to breadth first search. So breadth first search is this whole visiting neighbors and visiting the neighbors of the neighbors and visiting the neighbors of the neighbors. And the way it works is that it uses just a queue to do this. Essentially what you do is you visit, you have your starting node. I use S, they'll use 0 as their starting node. But you can use any arbitrary node as your starting node. And then you throw the neighbor, you look at your edges. So you look at 0's edges and you throw 0's neighbors into a queue. So you visit 1 and 3. Okay, and then you write down the guy you've started at. Okay? And then you're done. And you just keep repeating this. You remove from the queue. You move your first node from the queue. He goes into your visited sequence. And then you can go and start, and then you look at 1's neighbors because he used the guy you just removed from the queue. So we would add 2, 4, 6, and 7 to the queue. And then we're done visiting 1. And now we remove 3 from the queue. Okay, we look at all of 3's neighbors. And 3's already, we've got 0 already and 2 already. We've already seen them, so we're not going to bother with them, right? And then we're going to look at 2's neighbors. So then 2's next. We look at 2's neighbors. 1 we've already seen, so we don't bother adding it to the queue. 3 we've already seen, so we don't bother adding it to the queue. But we haven't seen 8 and 9, so we add them to the queue. Next is 6. Not 8 and 9, but we go to 6 next. But notice what happened. We looked at all of 0. Because we looked at 0, then we looked at 1 and 3 because 1 and 3 were his neighbors. Now we're looking at 2. Well, now 4 is next, not 6. I jumped the gun there. 4 is next. Okay. And then 5 is the only vertice that we haven't seen there, so we add it to our queue. But we've already seen 6, 1, 7. We've already seen 6, 1, and 7, so we don't add those again, right? Ideally, the way this works is that we use essentially 3 data structures, right? Instead of doing this coloring thing, we use a queue to determine what we're going to next. Okay. Then we use a set to say, have we seen this node or have we seen it not seen this node? Some people, with their node classes, they like to make a color and then use color to say the status of whether they're visited or not. I don't like to assume anything about the nodes I'm getting for my algorithm, so I just keep a set of nodes I've seen, right? And then I'll have a list for my output for the sequence in which I visited stuff. So I would use a set rather than a color here. So next node is 7. 7 we've seen everything that it's a neighbor of. 8 we've seen everything it's a neighbor of. 9 and then 5. So our visit order was 0, then 1, 3, so 0's neighbors. Then 2, 4, 6, and 7, which were the neighbors of 1, right? So 1 step away. Then notice how 4, 6, 7, and 2, they are all 2 edges away from 0. And then 5, 8, and 9 are all 3 steps away from 0. That makes sense to everybody? So this is a handy algorithm. So take an arbitrary, so for your algorithm, you're typically given a graph, or you're given a graph and a starting node. Either way works. When they say market identified or market visited, just add it to a set that you call has seen. All right, so I have seen this start vertice, and I put it in the queue. While our queue is not empty, take a vertice u out of the queue, right? Take it out of the queue and add it to the stuff you've seen. For all vertices adjacent to the node you're currently at, if you've not seen it yet, well, now you have, put it into the queue and continue. Right? And then putting it into your set putting it into a set like that means you won't double visit any nodes. Okay. What's cool about this is that you can use this to build a tree, to basically say how far away things are and see where basically everything is in the visit order. So we had 0, then we had 1 and 3, and then 1 was connected to 2, 4, 6, and 7. So this is kind of the way it visited everything. And then 2, then we visited 8 and 9 from 2, and we visited 4 from 5. Now, what's really cool is that we can use this algorithm, refer search, in an unweighted graph to find the shortest path from one vertice to another. So specifically, we use this algorithm to find it from the shortest path from the starting node to all the other vertices. So the shortest path from 0 to 1 or 3 is just to go to 1 or 3. The shortest path to get to 9 is to go to 1, then 2, then 9. Now, yes, 1 and 3 and 9 would have worked. 0, 3, 2, 9 would have worked just as well. But we are looking for, there can be more than one shortest path. When we look for a shortest path, we are looking for a shortest path, one that has that. So using one of the tied ones is just a valid answer. Let's go ahead and do one on the board, because I feel like this is pretty valuable. If we're let's see. So I'm going to use, again, my 3 data structures here. So I'm going to use a set called has seen, or a set maybe called just seen. And then I'm going to use a queue called Q. No need to be, we all know what the Q means. It's a Q here. It's not something like P and Q, which are easy to confuse in equations in mathematics. And then we'll use a list. I'll call it output just for simplicity's sake. And now let's create a graph. So starting location A, B, then C, D, Z, and C. And let's go ahead and look at, I'll put a Q here as well. Sorry, no, I already have a Q for my Q, so let's not make that too confusing. Let's call it L. Okay? So, so I'm going to use S just as my starting location. In Jung, if you're given a graph but not a starting node, you can get your list of vertices, turn it into an array, take the vertice at index 0 of that array, and you've got a starting location. But generally, you're fed a starting node. So I'm going to take S, and I'm going to put it into my queue. And obviously, since it's the first node I have, it's my starting location, I'll say I've seen it. So, okay, so I've seen S. So now I pop it from my queue. I add it to set C, to set if it's not already there. Okay, and now I add all of S's neighbors to my queue and to my scene. So I look at this guy. Have I seen him yet? No, I have not. Add him to scene, add him to my queue. Have I seen this guy yet? No, I have not. Add him to my scene, add him to my queue. Oh, and I forgot, I'll do that at the end. Have I seen this guy yet? Right? Have I seen this neighbor of S yet? Have I seen this guy yet? It's not in my scene, so I'm going to add him to here. I'm going to add him to my queue, and then I've looked at all my neighbors, so I'm done. We're done visiting me. Okay, we're done with me. Next, we need another node. So is the queue empty? No, it is not. So let's get the first thing off the queue. Okay. All right. Okay, so now we need to look at A's neighbors. So have I seen D? No, I've not. So add it to the queue. Have I seen B? Yes, I have, so don't add it to the queue. Have I seen S? Yes, I have, so don't add it to the queue. Okay, let's go. Okay, next, so I'm done with A. Let's look at B. Have I seen, so I'm at B. Have I seen B's neighbors yet? Seen A, seen S, so I'm done with B. Okay, what about C? I've seen S. I haven't seen L, though, so we'll add that. And I haven't seen Z yet. So I'll add those to the scene and queue. I'm done with C now. So now to pop off D, or sorry, DQD. So have I seen A yet? Yes, I have. Have I seen Z yet? Yes, I have. So I'm done with D. Okay. Now we're at L, right? So DQL. Have I seen L's neighbors yet? I've seen its only neighbor, which is C. So I'm done with L. And now DQZ. Have I seen Z's neighbors yet? Yes, I have seen D and I've seen C. So I'm done with Z. Okay. Do I have anything left in my queue? No, I do not. So I can output this list. And this is the list at which I visited stuff. Right? This is the order in which I visited stuff. Now, depending on what you're doing with breadth first search, your output might be different. I'm just simply outputting the order in which I visited stuff, which actually happens to be the order I saw stuff, right? But you might be using this to construct like a tree from this graph. So your tree might be an output in some other implementation of breadth first search. But the point is that all implementations that use breadth first search use the same basic algorithm, which is that I go through and throw my neighbors into a queue if I haven't seen them yet, and then I just dequeue the queue and then add them to my output as I go through. Okay. How long does this take? So how long does this algorithm take? Well, I looked at every node, right? And then for every node, I looked at all the neighbors, right? So essentially in an undirected graph, right, I was looking at every edge twice. I looked at it every time I first discovered a node, and then I looked at it the other way around, right? And if this was a directed graph, so, imagine for the sake of argument, each of these undirected edges were directed edges that were just two-way, right? Then essentially I looked at every single edge that exists in the graph. Well, that existed in the graph. So this algorithm takes the O to the number of edges, right? We essentially did one operation for each edge. Two if you count like doing this and then checking this way. But there was a number of checks equal to the number of edges. That makes sense to everybody? Right? It's fairly intuitive, so it's kind of hard to get into it the detail too much. So depth first search isn't that hard because all we're going to do is that I'll use the same example over here when we move off the slides. But the difference is that I'm going to use the same algorithm except of dequeuing this queue, we're going to be popping off a stack. Make sense? Same algorithm, but obviously the order which we visit stuff is going to change because we're going to visit what's ever on top of the stack rather than what's at the front of the queue. So for depth first search, what we do is we start a node. We process that node. So sometimes we say visiting the node, sometimes we say processing the node. In other words, we do what we need to do with the node. What we need to do with it depends on the algorithm that we're implementing this on. Right? So this is a bit different, right? Normally when we're talking about algorithms and stuff or traversals, we just say like print it out or just add this to this. Here we're saying we have a general algorithm that you're probably going to have to modify based on whatever you're doing with it. Right? So here we're just going to start at a vertex. We're going to process that vertice, and then we choose one of its neighbors. We don't look at all of them. We just look at one of the neighbors. And then we visit that one, and then we repeat until we hit a dead end, and then we back up. And then if we're at a dead end at that point, we back up some more, right? So here is an example of that. So we're going to start at node 0 again, and we are going to, so found 0 first, then we're going to go and look at node 1, right? We're just going to choose node 1 to visit next. Then we're going to look at node 3 to visit next. We're just going to choose, right? So we go to 1, we choose one of 3's neighbors. We're not going to choose 0 again because we've already seen it, right? Then we're going to go to, well, now we have to choose one of 3's neighbors, right? We can choose either 0, we can choose either 1, or we can choose 4. Well, we can't choose 0 because we've already seen it. We can't choose 1 because we've already seen it. So we choose 4. Now 4, we look at all of its neighbors and we go, hey, we've seen all these guys before. So I'm at a dead end. So I'm done. So let's backtrack to 3. So we backtrack to 3. And 3 goes, well, I'm done because I can't go anywhere else. 1 goes, I'm done because I can't go anywhere. I can't go anywhere new from here. So we backtrack all the way to 0 and go, well, we actually have another option. We went to 1. Well, we can now go to 2. And from 2, we can go to 5 or 6. We'll choose 5. And then from 5, we can go to either, well, we can only go to 6 because that's the only unvisited one. So then we're at 6, and we're at a dead end. So we back up, we back up, and we back up. Right? We were at 6, then we're at 5, which is a dead end. Then we're at 2, which is a dead end. And now 0 is a dead end too, so we're done. Okay, so there's 2 orders that you can go through stuff, which is the order in which you visit the nodes, right? The order in which you literally go through. And then there's also the finish order, which is the order in which you backtrack, right? And so there's this concept basically that we have, we have this discovery order. We have 0 to 1 to 3 to 4. And then we can represent all the other edges we don't have as something called back edges. Essentially, we can create a tree, and then anything edge we didn't use to go through the tree, it's kind of like it's a tunnel that leads from those nodes to back up through there if we needed to. So now the algorithm they use, they do it recursively. Why can they do it recursively? Well, because guess what? Stacks are what you use for recursion. So I'm just going to happen to use a stack because it's easy to modify breadth first search with and turn into depth first search if you use a stack instead. But here's the algorithm. Mark it visited. Then for every vertice adjacent to your vertex, if you haven't seen it yet, set the parent of V to U in case you want to keep track of how you got from where to where. How would you do that? Set a parent up if you didn't keep that in the node. Use it as a map, right? Given a node, the key of the node is the node, and the value of that is its parent. So you can use a parent to keep track of. You can use a map to keep track of your parents if you really want to. Again, you modify this algorithm. You don't necessarily need to do this. You just modify the algorithm if you do, and then you just do recursion. So let's look at this though without recursion, and just in a similar way that we would process. And again, I'm not going into too much detail on this because your homework for this week is to figure out how these things work. They aren't the most complicated of algorithms out there. In fact, they're very standard algorithms, very basic algorithms. But I wanted you to basically get a chance to tackle them yourself and learn how to use your graph library. So they're simple problems, but using the graph library might make it a bit tricky. So we're going to start at S again. Okay, so we're going to put in our stack. Okay, is our stack empty? No, it's not. So we pop off our stack to see what we're visiting first. Okay. Now we need to choose one of S's neighbors as the branch we're going to go down. So what neighbor do you want to go down? A, B, or C?
A.
A. Okay. So we'll choose A as our as where we need to go down. Actually, sorry, we don't need to. Yeah. So we popped off our stack. That's fine. So we're at A. Okay. Then we need to choose. So okay, we've seen A. Now add it to the stack, and now go to. Now we need to choose one of. Sorry. Now we need to pop off A. Pop off here, or no, we only pop off when we backtrack. That's right. So S A. Okay, so now let's choose one of A's neighbors. Okay, so B, we're gonna choose B as B. Okay, and now we're gonna choose one of B's neighbors. Does B have any new neighbors?
No.
No, it doesn't. So what do we need to do?
Backtrack.
We need backtrack. So we pop off B. Okay, now we're at A. Choose one of the A. Are we at a dead end yet? Nope, we can go to D. So we add D to the stack. Okay. Are we at a dead end with D? Nope, we can go to Z. Add Z to the stack. Are we at a dead end at Z?
C.
Nope. C, we can add C to the stack. Are we a dead end at C?
L.
We can add L to the stack. Are we a dead end at L? Yeah, we're at a dead end with L, so we pop off L. We're a dead end at C, so we pop off C, we pop off Z, we pop off D, we pop off A, and then we pop off S because we're done. We can't backtrack anything else. And notice that it would be a very different, we'd have to do multiple backtracking operations if we went S, C, L, right? Then backtrack to C, and then, it would be a different there's a different order to go around. Yes?
Now, when the algorithm's taking place, is there anything that would determine whether your first move would be from S to A or from S to B? Like imperative?
So on exams, what we would do is that we would say break ties alphabetically, typically, on an exam. But in programming, you just take whatever the next one is. So whether you're just iterating through the array list or you're iterating through the matrix, you just choose whatever the next one is. There's no real, there's really nothing that, and when we're looking at it, I just say choose one, please. Make sense? So depth first search isn't too tricky. So, and we've done depth first search too, as well when we've gone through, like when we did our maze kind of, when we did our maze thing, that was actually us doing depth first search. You've already solved depth first search when we went through the maze. So let me boot up. Their maze is silly. I'm trying to, hopefully, yeah, I'm booting up IntelliJ so we can look at our maze. Assuming I can find my solution in here because I reinstalled IntelliJ and then, of course, that uninstalled everything that I installed. But so let's go ahead and I don't need tips. I mean, I probably do, but I don't need them right now. So open project, teaching. Yeah, teching isn't teching, teaching. There we go. New window. So destruct assignment stack maze, right? When I went through, right, when we went through, set up SDK. Okay. So when I went through this with you guys, I'm sorry, when I did this, it was, we're solving the maze, it was, right, while the stack isn't empty, right, instead of using edges, right, we didn't explicitly say edges, we just used a grid. But really what we had was, do we have an edge to our north? Do we have an edge to, do we have an edge to the north? Do we have an edge with the south? Do we have an edge with the west? And do we have a edge with the east, right? East wall, not having a wall between us meant there was an edge between those two squares. That made sense? So that's, so when we went ahead and ran this, we were doing a depth first search. Let's see, can I please, oh, right, I run the maze. I run this class to run it. So let's go ahead. It's building the project, so it might take a second, right? Now it's running, right? So when I ran this class, right, what it was doing, this is a depth first search where basically it checked going, can we go north, east, south, west? And basically we tried this tunnel and then we backtracked to the next square, and then we backtracked over here, and then we backtracked over here, then we explored this entire branch and found it was a dead end. Then we backtracked up to here, right? And we go ahead and lower that to maybe 10 by 10 so that it's easier to see the grid, right? But all this was a depth first search, right? We went down this branch, we backed up, we said, oh, there's a branch here, go down this branch, no, that's a dead end, go down this branch, no, it's a dead end, so we have to back up all the way to be over here, right? And the difference is that we're just using squares rather than nodes and edges here. But this is a problem you've already solved. So hopefully that gives you some comfort into this, right? Now, the other thing to note is that we can use def first search on mazes. So maze def first search to not only solve a maze, but also to generate the maze. Like, oh, here's a graph theory. Here's basically a, graph maze where it's just checking out stuff. Let's see more details. So this one is creating a maze for us. And it, just simply was choosing nodes and vertices until it hit a dead end. Here's another one that uses depth first search so once it hits a dead end, it backtracks, which is in blue. Right? Once it kind of just gets itself into a dead end, but it's randomly choosing a direction and then backing up. So this creates a maze that's depth first search. Now, depth first search based mazes, they typically end up being windy like this. Notice that basically this one has long winding corridors without too many branches, right? That's the big thing here, is that those corridors are just very windy. And then there's other things, but mazes are very interesting in that way, but you can use depth first search to create a maze. All right, so I'm going to skip the topological sort because I like coming back to that last. So, and now we get into the obligatory portion of learning graphs, which is that every time you learn about graphs, you learn this algorithm. Guaranteed. At least I did. Every class in my as an undergraduate that I learned about graphs, I learned about Dijkstra's algorithm. Every class in my graduate education that I learned about graphs, I learned about Dijkstra's algorithm. It was just assumed that you should know this, and that they couldn't assume that it had been taught in the other classes for some reason. So everybody teaches it. So we've been working with unweighted graphs, right? Depth first search and breadth first search. They answer questions about if we don't care about weights. But normally, a lot of times we care about weights. Like, let's look at this example, right? So now let's go ahead and add weights to all these. 5, 2, 1, 7. Let's actually make this a 2, a 1, a 2, and a 7, and a 5, right? And the question is, what is the shortest path from S to L? Right? What is the shortest path to S to L? Question is, and so what would our algorithm be? And you kind of just look like, okay, so S to L, right? The direct line is take, go through C, so that would be a total of 12. But maybe if I go around this way, S to A, that's 5, 7, 8, 9, 10, that's 15. But if I go 1, 2, 3, 4, 5, 6, 7, 8, so this way is 13, right? So the best way is to go directly, right? But what if we lower the costs over here to all ones? Then the shortest path isn't 12. It is 1 plus 1 plus 1 plus 1 plus 1, 5 plus 5. So it's 10. So shortest path problems are pretty important because, you want to save money. If we're talking about like, if this is the cost to get from one place to another. It's also important if you're driving to figure out that, to make sure if your GPS routes you on the shortest route. Now, as you may have noticed, Apple, Google Maps, and Waze, which is also owned by Google, happen to have different interpretations of what would be the shortest route. Waze tends to drive you through other people's living rooms, but but it's just they have different ways of calculating what the shortest route would be for you, and that gets really the reason for that is because things get really tricky when you're talking about adding things like traffic. So these costs don't necessarily stay static all the time. So we don't have to really worry about that in this case. What we're worrying about is stuff like, can you change can we get from one place to another in the shortest possible amount of cost? And Dijkstra's algorithm is pretty useful for doing that. It says, given this node, the starting point in a weighted graph, I'm going to give you not just the starting point to some destination. I'm going to give you the shortest path from this guy to all the other nodes. So essentially, this is a breadth first search over a weighted graph that gives you the best way and cheapest way to travel. There are some caveats, though. Dijkstra's algorithm does fail in a couple of key places. And the first is that we are not going to be assuming, and the main one is we're not assuming negative cycles in here. Now, what is the shortest path from S to L? S-A-Z-C. I can find one better. Anything you find, I can find one better. Yeah, anything you find, I can find one better, right? You get a net gain of -1 if you go S to A, then S to B, right? So 3 over here and then 2 over here. So I'm now at -1 where I was at 0. Go around that again, I'm at -2. Go around that again, I'm at -3. So Dijkstra's won't be able to recognize that. Very few. Another algorithm called Bellman-Ford will recognize it, but it doesn't know how to solve it. It will just simply yell at you and say there's a negative cycle in this graph. And a negative cycle means that we could go around it a bunch of times and, essentially rack up the cheapest cost we could, right? So the answer to this is that it's undefined, or negative infinity is my cheapest path. So Dijkstra's does not really know how to handle that, and explicitly just doesn't. Also, depending on what data structures you use on this, Dijkstra's algorithm can be really sped up. We're going to use now if you're taking 3223, when you go over Dijkstra's algorithm again, you will be learning about the way that the optimizations, like using keeps and stuff to speed this up. Right now, we're going to use Dijkstra's original implementation as written in a while ago. So the hardest part about Dijkstra's algorithm is actually spelling his name. So that's D-I-J-K. Dijkstra's. Right? And first thing, and if you put Dijkstra up, let's see. It comes with Esker Dijkstra, the person, the computer scientist first. And then the next thing is Dijkstra's algorithm. The third thing is a YouTube video about Dijkstra's algorithm and how it works. And Dijkstra's algorithm has a animation here on how it works. Let's see if it has more animations. Yes, it does. It's got plenty of animations over here. Dijkstra's algorithm is very well known. It was created when? 1956, published 3 years later. And then later, they've managed to speed it up using a min priority queue implemented using a Fibonacci heap, which is a special type of heap. And that ran in the number of edges plus v times, plus the vertices times the log of the number of vertices in 1984. And it's essentially one of our best algorithms here. Now, there's a lot of other algorithms here. A-star is like the classic one you learn when you're learning AI, which uses a heuristic to estimate the direction you're going. There's Beam. Bellman-Ford is another one I just mentioned, right? Which is the amount of time which again finds the shortest path. But there's a ton of other algorithms over here that basically work. That are graph and tree search. A-star is a big one. Dijkstra, Bellman-Ford, Kruskal you'll probably learn as well eventually. But here, where our goal is to learn Dijkstra's algorithm. And the algorithm that we're going to use runs in v squared time, which is the number, so number of nodes you have. Okay. So, and we're also going to learn it the way that Dijkstra originally put it, only which used arrays and sets, which are kind of poorly named. It has S, which is the nodes that we have the shortest distance, that we finished with the shortest distance for. VS, which is the nodes we still need to do. Then you have an array called D, which contains vertices, and that's the shortest distance, and P, which is the predecessors, right? So you've got S, VS, D, and P, which really are kind of terrible names, so I'm not going to use those names, okay? If you've got terrible names, I'm not going to use those names. I'm instead going to use, when I write it on the board, I'll use done, to do, distance, and pred. Dist and pred, right? He's coming from the 50s as a computer scientist, which means he has a mathematical background, which means he puts down variables like a mathematician, rather than as a computer scientist who says, I can use more than one letter for a variable, okay? Which you should. So Dijkstra's algorithm says we want to basically start from this node 0 and compute the shortest distance from node 0 to all the other nodes. So it's going to be our starting vertice. And we automatically know the distance from our node from the starting vertice to itself, right? Which is 0. VS is all the other nodes. So we're going to put 0 in our start set, in our done, and all the other nodes in to do. Here's our list of vertices. Here's the distances, the shortest distance that we have currently computed to these vertices. So what we currently know is the shortest distance and how we got there. Okay, our predecessor, the last person we saw there. Okay, so we start out by saying, okay, we know the shortest distance to the start point. It's you stay there. Okay, and then to do, these are all the other nodes we have to figure out our point for. Okay, let's go ahead and do laser pointer because I'll bring it up. Now we got to figure out our initial distances to all these nodes. All right, so initially I know that at 0, it costs me 10 to get to 1, it costs me 30 to get to 3, and it will cost me 100 to get to 4 if I just start from looking at 0. That makes sense to everybody? So I'm going to go ahead and populate that. 10 to get to node 1, 30 to get to node 3, and 100 to get to node 4. And I'm just going to go through this, and you kind of get the feel of how it works before I explain the algorithm. Once you start to pick up on it, essentially. So these guys, right? Right. So I set their predecessors. Oh, sorry. So before I do the predecessors, right? How did I? So I got to 1 this way, I got to 3 this way, and I got to 4 this way. Now I can't get to 2 from 0 directly. So I'm going to say that for anything I couldn't get to directly, I'm going to say, as far as I know, the distance to get there is infinite. Make sense? Could get to those guys directly. Infinite cost to get to 2 right now. And then I got there just from our starting node, which is 0. Okay, that's how I got there. So I can get. So right now I know if I can get to node 1 with a cost of 10 from 0. I can get to node 2, but it's going to cost me an infinite amount of currency to get there from 0. And it cost me 0. So it cost me 30 to get to node 3 from 0. That's probably the reason why I use letters. All right. So now what we do is that we look at all the distances of the nodes that we haven't figured out the shortest distance to, and we figure out which one we currently have as the shortest distance. So 10 is the smallest, 10 is smaller than infinity, 10 is smaller than 30, 10 is smaller than 100. 10 is the smallest item. So that's going to be our next. So our next node is going to be 1. Okay. At this point, since we can say we figured out the shortest distance to 1. So now that we know the shortest distance to 1, we're going to use its information to update our information to get the other nodes. So we're going to look at all the nodes that are adjacent to 1. What nodes are adjacent to 1? 2 is adjacent to 1. Okay. So it cost me 10 to get to 1, right? We know that from my table. And it will cost me 50 to get to 2. So from 1 to 2. So let's look at that. That's 10 plus 50. Is that smaller than infinity? Yeah, that is. So I've now found a new shortest path. So I found a shorter path to 2. We don't know if it's the shortest path to 2, but it is a shorter path to 2. So we'll put in 60 as the distance, and we say we got to 2 with a cost of 60 by going through 1. Okay, how did we get to 1? Well, how did we get to 1? We went through 0. So you can basically look at the predecessors and chain them together to know your cost. And the number here, that's the total cost to get there. Okay, so now we're done with 1. So we found the shortest distance to node 1. So we move it into our done set. So now we go through all the nodes in our to-do set. So 60 is currently the smallest, but 30 is actually the smallest distance that we found so far. So that's the next node we're going to work on. Make sense? So we look through our to-do and find the one with the smallest distance. Okay? So now we look at all the nodes going out of 3. So let's look at, so it costs 30. So let's look at the edge 3 to 2. So it costs 30 to get to 3. And then it costs 20 to get to 2. That's 30 plus 20. That's less than 60, which is the current thing we know how to get to 2. So we'll go ahead and update 2 and say, actually, our shortest distance to get to 2 now is 50 by going through 3. So now let's look at going to the other adjacent node. So we looked at 3 to 2. Now let's look at 3 to 4. So 3 to 4, right? You had 30 over here plus 60. That's 90. And 90 to get to 4 is cheaper than we currently know to get to 4, right? So we update and say, hey, 90 is less than 100. So we update that. So now we're done looking at 3. Now let's look at node 2. Right, because we look at the nodes that we have left. We have 2 and 4. It costs 50 to get to 2 and 90 to get to 4. So let's look at 2. That's got the shortest distance so far. So let's look at the total distance. It cost me 50 to get to 2, right? Because we had that 30 plus 20. But for the simplicity of the algorithm, we don't retrace the whole step. We just simply look at our table and go, oh, it costs 50 to get to me. So plus 10 to get to 4 is 60. So this is the current distance to 2 plus the weight of 2 to 4, that's 60. Is that less than what I currently know of how to get to 4? Yes, it is. So I update it. And I say the cheapest way to get to 4 now is 60, and it costs that, and we do that by going through 2. Make sense? And we remove it from the set. And then the final vertex is 4. It does, and because it's the final vertex, it's not going to have any ways to go to anywhere. So we're done with it. So the algorithm is this, and it looks like a lot. I recommend instead of using sets and arrays, I recommend using sets and maps here, right? So initialize S. Let's not call it S. Let's call it done with the start vertex, and to do with the remaining vertices in the graph. So for each node in and why does it say for all and not for each? Well, because we're coming from mathematics where we use that the upside down A symbol essentially as the for all. So for all nodes in to do, we set the parent. We use that map. We set the parent to the starting node, and if there's a node from the starting node to that node, we set the distance to that weight. Otherwise, we set the distance to infinity. Now, while you still have stuff in your to-do pile, for every node in there, find the one that's, look at all of them, find the smallest one. Remove that guy from your to-do set, add him to done. Okay, that guy you just added to done, check all of his adjacent vertices. If it's cheaper to get from that guy that you found the shortest distance to any of the other nodes, if that changes any of the prices to get to the other node, update that price in that parent. So let's look on the board. So I'm going to need a couple of new data structures here, and I'm going to need I'll make a new graph of this one. So we've got S, A, B, C, Q, T, R. Okay, so let's do that. Again, I just kind of make this up as I go with these graph examples. Maybe I could use a better one, but honestly, we can just fiddle around with costs and stuff. So let's go ahead and put a 10 here, a 5 here, 1, 3, 1, 2, 8, 4, 6, and 12. Okay? And I just choose interesting numbers like that just so we can simply set it up. So, right, they had an S and a VS. I'm not going to use those terminologies because I like using nice consistent variables. Done, right? And we're going to start out with in our done set, S, where we're going to start from S. Obviously, if we chose a different one to start with, like T, our answers would be different. But I'm just using S as our starting node. And then to do is what? We've got A, B, C, R, Q, T. Okay? And then we had that table thing where we listed, so S, so we've got S, A, B, C, R, Q, T. Okay? And then we've got, so those were all of our nodes. And then we had our, instead of using arrays, I'm going to use maps again. So I'm just going to have a distance map, right? Where these are the keys, okay? And then what I'm going to put in here is the value. Obviously, the distance is just the weight. And here, instead for P, I'm going to spell out what it is, which is the predecessor, right? The guy I got there from. So it becomes a bit more understandable when you add those terminology. When you add that. Is it just a reflection that makes it hard to read up here? Yeah, but I mean, it makes it easier to see on there, but I don't know how easy it is to see the board.
Looks like there's more contrast with less time.
Yeah. So what do you guys think? Can you move the lights back there? Turn them on? Yeah. That's better, I feel.
I watched the videos and you can see them when the lights are on.
Okay, I'm just not sure. Is this fine for everybody though? Yeah. Okay. Because I just wanted to make sure. So okay, we've got our starting node. So the first thing we need to do is set up our initial distances. So right, that's the first part of our graph, basically. So we did this already, initialize S with the start vertice, are done with the start vertice, and then we put everything else in here. So for all the vertices, we need to set the predecessor to, and right here for this node, I'm just putting our start node just for completeness, but we don't really care about it. Then everybody else, they get, they're getting S as our predecessor. So S is your predecessor, right? And then for the distances, we need to look at this and figure out what our distances, our initial distances are. So S is connected to A, B, and C. So it costs 5 to get to A. S to A is 5, S to B is 1, S to C is 2. Okay. If I get a tie, I'm just going to break my ties alphabetically. Okay. And then for these guys that I can't get to directly, I just put a cost of infinity, or you can put a, yes, because that you want to put double dot positive infinity in there. Okay. All right. So let's go ahead and look at, so now what is our algorithm? Well, for each of the to do, we look at them and find who has the shortest distance. B has the shortest distance, which is 1. Oh, I've run out of time, haven't I? Wasn't even paying attention to the time. Wow. Okay, so we'll pick up here on Wednesday, obviously. My bad about that. Obviously, this would take more than one algorithm. More than one step to solve. So.